So good morning, welcome to the microelectronics exercise 1. Today we're going to talk about the MOS technology and devices. So in the exercise sheet that you were given, the first question states to show a so that the figure 1 shows a cross-sectional cut through a wafer of a MOS transistor in a single weld process. It's asking you to write the proper type of doping in the respective boxes and name the terminals. Okay, we also have to differentiate between weak and strong doping. And we have to also mention whether it's a NMOS or a PMOS. Okay, so we have here the figure, and the first thing that we have to see, or that we can see, is that this P here represents that the whole substrate is a P substrate, it's a P-type substrate. So that means that if we don't do any well here, the transistor that we would have is very likely to be a NMOS. But the first thing that we have to actually do is, okay, so we know that we have a P substrate, but we actually have to connect this substrate somewhere. So the first thing that comes to my mind is to use this terminal here. So we're going to have to write a P plus here, like it's stated there. And the reason why it's strongly doped is to reduce the resistance for any connections. The next thing that comes to my mind is that we have to define, so we know that we have a transistor in the center of the figure. So we have to define the other two, whether these two boxes are N or P. So if we want to make a transistor in this case, we need to make them N. So it's going to also be highly doped. So we have already here the doping already. So we already wrote the doping in the respective boxes. After this, now we have to define what is the name of the terminals for this figure. So the first one that we already know is a bulk. The bulk is connecting the substrate to the outside. So we know that this terminal, highly doped P, is a bulk. The next one we can define whether this terminal here or this terminal here is an NMOS, is a drain or a source. So actually it can be either way, but just as an example, I defined the first one as a source. Then it's very straightforward where the gate is. So I also name the gate in the middle terminal. And then the last one, of course, is our drain. We now know that it's an NMOS transistor, and it's very easy to identify when is an NMOS and when is a PMOS if you see a sectional cut through a wafer. If you have a P substrate, which is the case right now, and your source or your drain, or I mean actually both of them are N-type, then it's very easy. We just take the N from here and then we put it in front of MOS, so we have an NMOS transistor. If we would have an N-type substrate, then of course we would have to have a P in both of these boxes, and then it would be a PMOS transistor. The next part of the first question is to connect the voltage sources U2, U1, and ground to drive the transistor into saturation region. So we have here these three voltages. And the first thing that comes to my mind is to connect the bulk terminal. So normally you should connect the bulk to the lowest potential in your circuit. And the reason of that is to avoid the parasitic diodes that can be created. Okay? So the first thing that we do is connect the ground to our bulk. We will have the connection. And now, so we need to have a source which has a lower potential, of course, than the drain. So then we connect also the source to ground. All right? Now, if it's set that the transistor has to work in a saturation region, then we have to know, of course, that UGS has to first be greater than UT. So we know our UT is 0.5 volts, So I think any of these two voltages are suited to be in the gate, since now my source is 0, so it's grounded. And then the next condition, in order to be in saturation, is that UDS has to be larger than UGS minus UT, right? So now, in order to have a larger UGS minus UT, then we can do connect, let's say, the UDS to the highest potential. So we do it here to a 3.3 volt source, and we connect our gate simply to the middle potential, which is 1 volt right now. In this way, we ensure that we are operating in saturation region. Now, the next question asks you to sketch a cross-sectional cut through a wafer of two complementary transistors. That means NMOS and PMOS. There is a mistake here in the exercise. Actually, it should not have been in a double well process. It should have been in a single well process. Additionally, draw the appropriate channel shape, assuming the NMOS operates in saturation and the PMOS in linear region. Okay, so we have here a single well process. You have one well here, and that's why it's called single well process. The first thing, again, as the previous one, we are going to select select the doping of our substrate. Just because it's more common, I'm gonna put a P in the substrate. So it's gonna be a P substrate. And then in my well, I have to also define a doping. So if I have a P here, then it's obvious that the next one will be an N type well. Then to continue with the previous, so the same way that we did it in the previous part, we first search a connection from this substrate and from this well to the outside. So the first, we put a P plus here, and then this would be our bulk connection. Okay? Then we go to the well, and then we put an N plus, because we have an N-type well, and then we call it also our bulk. So that means that this is the bulk of one transistor, this is the bulk of one transistor, and this is the bulk of the other transistor. The next thing that we can continue on is determining where is our gate, source, and drain for both of the transistors, right? So if we already know that this is a p-dope substrate, that means that this transistor in this side will be an NMOS. And therefore, I have to add an N plus doping in this terminal, and then I also add another N plus in this terminal, and then since we have here a N well, then I, of course, analog to the previous one, I put a P plus and P plus in this box, all right? Now I defined this as my source. Of course, this is the gate, and then the next one is the drain. We identify very clearly where the gate is of the transistor inside the well. We define this terminal as our drain, and we define this terminal as our source. All right, and finally, again, as I already stated, since we have a p-dope source and a p-dope drain, this means that this is a PMOS, and in this case we have an N-dope drain and N-dope source, so then we can easily say that this is an NMOS. The next part, it says to draw the appropriate channel shape assuming the NMOS operates in saturation region. So in order to operate in saturation region, you should be at least in pinch off. So that would mean that our channel is a little bit, so it's not completed. So this region has no channel. So our channel shape looks like this with negative charge carriers. For our PMOS in linear region, we have no pinch off. So we have such channel shape. The next part of your exercise asks you to write the current equations for all regions and the corresponding biasing conditions. Okay. So first, we know that this is the how an NMOS transistor looks like. I think in your exercise it's not called figure 1, but it's called figure 2. And then our first condition is when VGS is smaller than the threshold voltage, that means, at least for the scope of this class, that means that our transistor is off, so that means nothing is happening, and therefore we assume for the microelectronics class and possibly also for the analog CMOS class that the drain current is going to be equal to 0. I have to state that this is not completely true for all cases. There are some people that actually work in the subthreshold region, but the details of the operation in subthreshold region is not the scope for this class. So it's as simple as when VGS is smaller than VT, then you have 0 current flowing. We call this equation the subthreshold region. Or cut off. All right. The next region, when we first have to know, is our transistor on or not? So the best way to see it is that VGS is larger than VT. After that, we have an additional constraint, and this means that the drain source voltage is smaller or equal to the gate source voltage minus the threshold voltage. And when these two conditions are true, so the first one, this one, and the second one, this one. When these both conditions are true, then we are operating in the linear region, and the formula for the linear region is this one here. Now our third condition, or third region of operation, is the saturation region. We first check that our transistor is on, so always check that your transistor is on, because maybe you start doing a lot of calculations and your transistor is not even on. So check that your transistor is on, and then the big difference with the previous one is the sign. So in this case, the drain source voltage is larger than the gate source voltage minus the threshold voltage, and the formula is this one here. In the part B of question number 2 asks you to label the transistor type, whether it's a PMOS or an NMOS. Label all terminals, currents, and voltages in figure 1. Actually, should say figure 2 in your exercise sheets and figure 2. All right. So this is now the symbol of a transistor, and the first thing that it's asking us to do is whether to determine whether it's a NMOS or a PMOS. So when you see an arrow pointing towards the inside of the transistor, and this is in the middle, so you have the arrow pointing to the inside, and this line is in the middle, this means that this is an NMOS transistor. Okay. This is only a convention. There is also different symbols for a transistor, and for different types of transistors that you may have some arrows here, for example here. There's different symbols that you can see in the internet, but for this class we're going to use this one. All right. All right. The next part of the question is to label all terminals. So it's very similar to the cross-sectional form. This one is going to be your gate. This one here, just because our current is flowing in this direction, we're going to consider this one is our source and this one is our drain. If the current was flowing in the opposite direction, then you can also consider that this one is your source and this one is your drain. Okay? And finally, you have the bulk connection here. Now for the voltages, the voltage between here and here is called UGS. We have a voltage between the source and the bulk when they are not connected together, which happens pretty often actually. And this is called the source bulk voltage. And you have finally the voltage drop between drain and source, and this is UDS here. Now this is a calculation exercise. This is the third part of the second question. And they are giving you beta, they're giving you the threshold voltage, they're giving you the dimensions of the transistor, the gate source voltage, and the UDS. Then they are asking you to calculate the current ID. All right? So the first thing we have to do is to know in which region is our transistor operating. So the first thing we check is if it's on. So UGS has to be larger than UT. In this case, our UGS is 0.5 volts, and our UDS is equal to our threshold voltage is here is equal to 0.2 volts. So that means that this condition is met, so our transistor is on. The second thing that we have to do is whether to check if it's in linear or in saturation region. So in order to do so, UDS, we don't know whether it's equal to something or if it's larger or not. And then we have UGS minus UT. Okay, our UDS is 0.3 volts, our UGS is 0.5 volts, and our UT is 0.2 volts. If we make the calculation in our head, so this is 0.3 volts, so that means that these terms are equal. All right, so now in which region are we operating? If you come back to the previous exercise, and you saw that these signs represent smaller or equal, and this one is larger or equal. That means that in this case now, both the linear and the saturation region meet the conditions. So our transistor is in exactly at the pinch off, so it can be calculated either with the linear formula or with the saturation formula. So first we calculated with the linear region formula, and I get an answer of 22.5 microamps. And then we calculated with the saturation region formula, and then we get an answer of the same. So both of these quantities are exactly the same. That means we are verifying that our transistor is actually at pinch off because both of the conditions are met. At the end, you can choose whatever formula you want to use the most. So it's up to you which formula you use if your transistor is at this pinch off. The fourth part of the question number 2 asks you to vary the voltage, the UGS, the gate source voltage, by plus and by minus 100 millivolts. So how much change in the drain current follows? So the first thing that we have to do again, so we already know that, okay, so we first analyze if our UGS, or if our transistor is on. So first, UG, okay, I'm gonna make first the case for plus 100. UG has to be larger, UGS has to be larger than UT. And right now, if in the previous exercise or UGS was 0.5, right now UGS is going to be equal to 0.6 because we're adding 100 millivolts, right? And this is still larger than 0.2, which is our threshold voltage. Okay, now UDS, which is 0.3, as you remember in the previous section. And then we have our UGS, which is 0.6 minus 0.2. I'm going to write it here, UDS, UGS, and UT. Now, if you calculate this is equal to 0.4 volts. That means 0.3 is smaller than 0.4. And what does this mean? That means that we are working in the linear region. Okay? So now we do again all the steps that we did before, and then we put everything into the formula, and then we calculate. Now we get 37.5 microamps. So the change in ID is plus 15 microamps. Now, if we do it for minus 100 millivolts, UGS is 0.4, and it's still larger than UT, which is 0.2. So this is UGS, and this is UT. All right? Now the next condition is that UDS, we need to know if it's larger or smaller or equal to UGS minus UT. So we put the numbers down. 0.3 volts is UDS, UGS now is 0.4, and our UT still 0.2. Okay? If you make the calculation of this part, then you would end up with 0.2. That means that 0.3 is of course larger than 0.2. That means that we are now working in the saturation region. Now that we know that we're working in the saturation region, we plug again all the values in the formula, and then I ended up with a value of 10 microamps. That means that the change of current is now a negative 12.5 microamp. Again, to continue with the part number 3, actually there is a mistake only here in the slides. So this is exercise 3 and this is figure 3. Shows a simple measurement setup. The current I is measured while the voltage U is varying. And the measurement setup looks like this. So you have a transistor. Oops, it's a little bit small, but it's okay. This is our source U. These two are connected. So what does this mean? That means that I have at my gate, I have the same voltage as U, and at my drain, I also have U. All right? So now how do we make the plot? So we are asked to sketch the dependency of the current I to the voltage U. By the way, I is the current that flows through here, so it's the drain current in this case, all right? So first, we have to know that when U it's smaller than our threshold voltage, our transistor is going to be off. This is the first thing that you have to know, all right? So that this would mean, if we make a plot here, so current I versus our voltage U. If we think that the current I is this one here, so this is I, this would also, so it's also the same as the drain current, all right? So I'm just going to call it U. And just because we also see that the voltage U is also present here, just for the sake of this example, I'm going to call it UGS here. But it can also be called UDS. All right? Now, when U is larger than UT, or transistor is on. But first, I'm sorry, I'm going to go back a little bit to this one here. So we are going to define, let's say, a potential UT And until this part, we have 0 current. All right? So this is our plot. Now, coming back to this one here, when U is larger than UT, what happens? So our formula, or in order to prove in which region it is, so it says that UDS, and then we don't know if it's larger or equal, so I'm going to put a sign here. UGS minus UT. All right? Now, what is our UDS? Our UDS is equal to U, is here. So U, and then in the other side, UGS, which is the voltage from here to here. Sorry, here is ground. I forgot to mention it. Our UGS is also equal to U. And then we have the UT. All right? So that means that our UDS is always going to be larger than U minus UT. Why? Because in this side we have this term here that we don't have in this side. In this side we only have U. So what this means is that the transistor is always going to be in saturation. Okay? And then if I relate to the formula of saturation, ID is equal to beta sub 0 divided by 2 W over L UGS minus UT square. All right? Beta sub 0, this is a material parameter, so we cannot change it. So we as designers cannot change this. So this is a constant. Or W over L, so we assume that the transistor remains the same size through this testing, so it's fixed, so it's also a constant. Or UT is also a constant, so it's defined by the material parameters. So the only thing that we can change right now into this experiment, or I'm sorry, that is actually changing in this experiment, is UGS, because UGS is equal to U, and U goes from minus UT to, I'm sorry, smaller than UT to larger than UT, so we assume that UGS is the only thing that can change. So therefore, the relationship between ID and UGS is the same as the relationship of I and U. And as you can see, you have a square here. So this would mean that after this point, after the transistor gets on, then we will have a kind of a square signal. So I am not a very good drawer, but this is supposed to be a square function. All right? Now the part B asks you to mark all the operation regions in your plot. So we already talked about it. So we divide our plot here. And we say that this one is in cutoff. And this part is in saturation. So I made a numerical example for you guys. And this is with a simulation. So this is more or less the same. We have no current flowing in this part. And then from here to here, it goes up. I'm sorry, this is not a simulation, this is a calculation. And this is what you end up with. Okay, so for question 4, this is really a simulation. So I took a MOSFET with a W over L of 100 micrometers by 100 micrometers. And in SPICE, I produced these plots. All right, so this is a drain current versus UDS. All right, or I should say UDS versus ID, but you know what I mean. It's asking first to label the different working areas in figure 4, and how is the border between the working areas called. So one very simple way of identifying in which region you are. So first of all, you can see that this top plot is going up from here to here, so around until here. It's going up, and after that it doesn't go up that much, so then it has a very small slope. All right, so then we also see that the slope of this part of every plot changes So this one is very steep, this one is less steep, less steep, less steep, less steep, less steep. Okay, so what we're going to do is when we're going to take some points, let's say until it reaches the flat line. So I'm going to just say it here. I'm going to take also this point here. I'm going to take around this point here, this point here, this point here, and around this point here. All right. Then cross a line here. And you see that to this side, the lines look very straight. So there is no much increase anymore. So you can increase your UDS a lot, but seems like it has no dependency. In the other way, this one, we can, it's arguable, of course, but you can arguably say that at least from this part to this part, it looks more or less linear. All right? So then it's a very straightforward. This part is a linear, and this part is saturation. Why? Because you have a linear increase, and then after that it stops. So let's say around here it stops changing anymore with any change in UDS. So after here it reaches a saturation in which it doesn't matter how much you change UDS, you're never going to get a lot higher value. All right? How can we see this with our formulas? So our first formula for linear region, we remember it, it's beta 0 W over L UGS minus UT minus UDS divided by 2, and then we multiply by UDS, right? Now you can see that in the linear region, the current ID has definitely a dependency on UDS. Maybe it looks like a quadratic dependency. It's not completely quadratic, but because if you put this term, this UDS term inside here, you also are affecting this term and this term. So yes, it's a quadratic with some additional influences, but you can see that definitely has an influence, the UDS with the ID. Whereas when we look at our formula for saturation, I have to also say that this is, of course, not considering the channel length modulation. All right. And now in this formula, which is the saturation formula, we don't have a term UDS inside this formula. Does it look familiar? Of course it looks familiar. This is what happens after this line here. All right? It doesn't matter how much we change UDS. This current ID is going to remain the same because it's only dependent on UGS and UT. Of course, UT is also a material parameter. These are also material and design parameters, so it would only change if UGS changes. To make it a little bit nicer, I put this plot over here. In this one, it's also show a sub-threshold region, which is this one here that is pointing here, which would mean that your UGS is lower than UT, so you would have zero current. All right, this is okay. It's obvious. So if in an exam something similar comes, you don't really have to write it. But we know that there is a sub-threshold region there. We know that after the current is starting to saturate, we have then these points here. And of course, this is called pinch off. So this, if pinch off is exactly the point, whereas if you go to this side of the pinch off, you're in linear, and if you go to this side of the pinch off, then you're in saturation. All right? The next part of the exercise asks you to extract the channel length modulation factor and the threshold voltage UT from the characteristic curves in figure 4. So just to remind you, figure 4 is this one here. And it also tells you to use the values marked in the plot and the formula for ID in the saturation region. Okay, so that means that we are only going to work in the saturation region, so we are going to work more or less from here to this side. And you can see that there is 4 points that I measured. All right, and we also have different UGS. All right, so this is the information that we have now. We of course have also our values for UDS. So from these points, we are supposed to extract the channel length modulation. There are 2 methods to do it. I would say one is correct, the other one is incorrect, but some other people can say that both of them are correct. So how do we do it? Well, we put our current equations, including the channel length modulation here, for a saturation region. And then what do? We select 2 points in the plot. We can maybe say, okay, first I'm gonna select for a line of UGS. So we select this line here. Okay, so we are gonna take only these 2 values from this line, so this value and this value. And we are gonna use also the UGS information. And then we make a division of current. So we have a current value here, and we have a current value here. All right? So a good mathematical way of doing it is to make a division of currents. So what happens? We are using the same UGS, so UGS is equal to 0.4, I think, if I'm not mistaken, yeah, 0.4 volts. So that would mean that this UGS is equal to this UGS here. Or UT, of course, remains constant because it's the same transistor. So that means that this whole term is constant, and this whole term is constant. All right? That means that if I have a division of these 2 terms, we can cancel these 2 out. And we are left only with this part of the equation. So this would be this part of the equation here. And the only thing that we have to do is to solve this equation for lambda. If you do some mathematical set of equations, then you end up with your lambda formula, which is going to be this one here. And then after that, you can just plug in the values that were provided to you. And then you end up with a lambda equal to 0.0043 volts to the minus 1. All right? The next question asks you to calculate UT. So for UT, we can make it in 2 ways. All right? We can select, okay, I'm going to work in one UDS, and then I'm going to select this point and this point here. So I'm going to work in this UDS, so selecting this point here and this point here. All right? I do the same division as we did before. In this case, our UDS remains constant. Okay, UDS is constant, or UGS is now not constant. If you want to check it, you have a UGS of 0.45 and a UGS of 0.4. So therefore, this term here is not anymore being able to be cancelled. However, I can assume one thing. Let's assume lambda is constant for different UGS. All right? That would mean that I can cancel this whole equation because my UDS is constant, my lambda is constant, of course, 1 is a constant. So I cancel these 2 terms, similar to what we did before. And we end up with this equation here. From this equation, we solve now to get UT, the threshold voltage, and you end up with this formula here. And we end up with a value of 0.187. Now, this is where it gets more interesting, I would say. So, is this result correct or incorrect? Well, we can actually do another method of finding UT. And then we can check whether this is true or not. All right? So instead now of choosing a specific UDS, what I'm doing now is I use only a single data point of the curve. I use the information that I already have from the channel length modulation, and then I just plug in. So I get my regular equation, which is this one here for saturation. And then I just solve for UT again, and you end up with this formula here. And then we chose in this case, I think this is the value that we chose. We chose this point here, so this set of parameters are chosen. So we plug in the values here. All right, we plug in the values here. Sorry, is this one here? We plug in the values in this side, and we end up with 0.183. So the previous one was 0.187. Are these two correct? No, they are not correct. I'm sorry, are they the same? Not, they are not the same. So where does the error come from? Okay. Before continuing and telling you where the error comes from, I have to go back a little bit and then tell you or ask you to remember that this is a 100 micrometer by 100 micrometer transistor. If we have a, let's say, 10 micrometer technology, that means that the minimum width of a transistor can be 10 micrometer. Then if you use 100 micrometer, it's a factor of 10 times. Nevertheless, a 10 micrometer technology, I would say it's very old. So, for example, the technology that we work with in the chair are 0.35 micrometer. And we also work with 0.18 micrometer. And let's just even go further to the Intel 22 nanometer process, okay? Now for these guys here, we're talking about a very big transistor here. So 100 micrometers is a lot compared to 0.35, right? So that means that we're working with a very large transistor in this case. In the next week's exercise, you will find out that working with large transistors, or actually you saw it in the class yesterday, that working with very large transistors affects you very little in the, so the channel length modulation affects you very little. Whereas when you have very small transistors, then the channel length modulation takes a big role. Okay? In this case, in our calculations, we have a difference of what? 3 millivolts, 4 millivolts, sorry. So okay, some people can say this is a lot. Some people can say that this is not so much. Okay? Nevertheless, you have to see that it's actually not the same. And the reason why it's not the same is because we made the assumption that the lambda at this plot and the lambda at this plot, they are the same. But in real life, they are not the same. So whenever you change a UGS, your lambda is different. So that means that the assumption that we take 1 point here and 1 point here and we simply solve for U cannot be done in this case. Now the last part is telling you that it is intended to use a transistor as a 3 microampere current source. You are supposed to calculate the gate source, the needed gate source voltage first when you have lambda equal to 0, and then from the lambda that we just calculated right now, so 0.183. All right. And then it also tells you that UDS is supposed to be 1. So UDS is equal to 1. All right? So what do we do? We need to find UGS, is the question. We have our ID, which is equal to 3 microamp. UT, we already have it from the previous exercise. And I'm sorry, I made a mistake. Lambda is not equal here to 0.83. Delete it from here. I think the lambda in this case was this one here. Yeah. It was this one here. So it's 0.0043. And our UT was 0.183. All right. So what else do we need? So if we make the first calculation, the beta given, the beta given 360 microampere over volt square. And the W 100 micro, and the L is equal to 100 micro. All right, so what is our formula? Formula again is ID equal to beta sub 0. This is intended to work in the saturation region, I think. Okay, so we have beta, we have W, we have L, we have U. I'm sorry, we are looking for UGS, so this is the question, and we have UT. So the very simple thing that you have to do is to solve for UGS and plug in all the values. And for the other one, ID is equal to beta sub 0 divided by 2 W over L times UGS minus UT square, and then you multiply this by 1 plus lambda UDS. All right. Again, we have UDS, we have lambda, we have current, we have beta, we have W over L, we have UT, and our UGS is our question. All right. So then now we plug in the numbers, and then it says that I need a UGS of 0.312 volts in order to obtain a current of 3 microamp. All right. Now if I go to the other formula, including the channel length modulation, we end up with this formula for UGS. I plug in all the data, and then I end up with 0.312. So these two values are the same. All right. So what does this tell us? This tells us that the consideration of lambda when you use very big devices has no further improvement in our calculations, since lambda, of course, is very small. Now I simulated this, and then I got a value at UDS of 1 volt. I got a value of 2.97. Okay, so we have an error of what? 0.03 micro. All right. So as long as this exercise is concerned, we finish. So thank you very much for your attention.